Redox reactions are probably the most important class of chemical reactions that take place in aqueous solutions. They're responsible for thousands of very important life-sustaining reactions, including photosynthesis and respiration. And as we shall see, redox reactions involve a transfer of electrons from one substance to another, and so they are also referred to as electron transfer reactions. We saw in a previous video that the reaction between an acid and a reactive metal produces a salt plus hydrogen gas, and the example that we used was the acid hydrochloric acid reacting with zinc metal to produce zinc chloride salt and elemental hydrogen gas. The equation shown here is represented as a full molecular equation. We can also write the full ionic equation by representing the ions as separate entities for the strong electrolytes present in the full molecular equation. We can then identify and cancel out the spectator ions to get the net ionic equation, where we have two H plus ions reacting with metallic zinc to produce the zinc 2 plus ion plus elemental hydrogen gas. And this represents the net overall chemical change that takes place. We also noted in the previous video that the substances in this reaction change their electronic charge, with elemental zinc starting with a 0 electronic charge and ending with a +2 charge, while hydrogen started as the +1 hydrogen ion and ended as elemental hydrogen gas with 0 net charge. It turns out that this change of charge actually equates to electron transfer processes between the reacting substances, where one reactant loses electrons from its electron cloud and the other reactant gains those electrons. And often in these redox reactions, the challenge is to track the electron transfer and determine exactly which substance is losing electrons and which substance is gaining electrons. To do this, we use the concept of half equations to help us out. So if we look at our net ionic equation, 2H plus Zn goes to Zn2 plus H2 gas, we can split this equation into two halves. For example, we can just focus on what's happening with the zinc, where we can see that the solid zinc is transformed to the aqueous zinc 2 plus ion. The only way this ionization process can occur is if the zinc atoms lose 2 electrons each. Loss of electrons is known as oxidation, and this equation is said to be the oxidation half equation. If we now focus on what happened to the hydrogen atoms, we see that the two H plus ions on the left-hand side ended up in the elemental hydrogen molecule on the right-hand side. Now, the hydrogen molecule forms from two neutral hydrogen atoms, and the only way that that can occur is if both hydrogen ions gained 1 electron each, or 2 in total. This gain of electrons is known as reduction, and this equation is said to be the reduction half equation. Early on in our studies, it's easy to get confused between oxidation and reduction, and which involves loss of electrons and which involves gain of electrons, and so on. To help us out, we use this useful mnemonic at the top right, oil rig. Oxidation is loss, reduction is gain. So oxidation involves loss of electrons, reduction involves gain of electrons. Oil rig. Remember that, and it may help to avoid some confusion in the future. Let's now take a closer look at these half equations. The first thing to note is the presence of electrons written in chemical equations, and this is the first time we have seen this. And you will typically only see this in half equations. The second thing to note is that both half equations are mass balanced and charge balanced. So what do we mean by that? Well, we can see in the oxidation half equation, we have one zinc atom on the left-hand side and one zinc atom on the right-hand side. So equal numbers and types of atoms on both sides. This half equation is therefore mass balanced. But we can also note that the total electronic charge on the left-hand side is 0. Elemental zinc atoms have no net charge, and the total electronic charge on the right-hand side is also 0, with the 2 plus charge on the zinc ion being cancelled out by the charge of the 2 electrons. For the reduction half equation, we see that we have 2 hydrogens on the left-hand side and 2 hydrogens on the right-hand side, so it is mass balanced. And we also see a net 0 charge in total on the left-hand side being matched by the 0 charge on the elemental hydrogen molecule. A couple more things to note, firstly starting with the oxidation half equation. When we write oxidation half equations, the electrons are written on the right-hand side to indicate that those electrons have been lost from the zinc atoms. In the reduction half equation, we can see that the electrons are written on the left-hand side, indicating that electrons have been gained. And this is another way of working out whether electrons have been gained or lost and whether we have oxidation happening or reduction happening. If you see electrons on the right-hand side of the arrow in a half equation, that is indicative of an oxidation process. If you see electrons on the left-hand side of the arrow in a half equation, that is indicative of a reduction process. Half equations can be summed together to give the full redox equation. If we were to add everything up on the left-hand side of the arrow in these two half equations and everything on the right-hand side of the arrow, we would see that these two electrons on the right-hand side would cancel with these two electrons on the left-hand side, leaving us with the full redox equation shown here. So redox equations are just an arithmetic sum of the respective oxidation and reduction half equations. And you will notice that because the electrons cancel out, we do not see electrons appearing in the full redox equation, and we never should. We should also mention at this stage that oxidation processes, loss of electrons, and reduction processes, gain of electrons, occur simultaneously, and so we cannot lose these two electrons without them being gained by something else. That's actually a consequence of the law of conservation of mass. You will remember that electrons do have a small but finite mass, so that mass cannot be lost. If one substance loses electrons, another substance has to gain those electrons, and that's why we don't see excess electrons left over on either side of a full redox equation. Now, another concept that we need to know about when considering redox reactions is oxidizing agent and reducing agents. An oxidizing agent is a substance that causes the oxidation of another substance. It is itself reduced in a redox reaction. So let's have a look at what that means. If we go back to our redox equation for the reaction between an acid and a reactive metal, we can see that these reactants, the 2H plus ions, have caused the oxidation of zinc metal to zinc 2 plus. And in that process, they have themselves been reduced from H plus ions to the H2 gas molecule. So in the sense that H plus ions caused zinc to be oxidized, we say that, in this reaction, the H plus ion is the oxidizing agent. If we look at it from another perspective, a reducing agent is a substance that causes the reduction of another substance, and it is itself oxidized in a redox reaction. So if we go back to our redox equation, acid plus reactive metal, we see that the zinc is the reactant that actually causes the reduction of H plus ions, and it is itself oxidized in the process. So since zinc has caused the reduction of H plus ions, zinc is therefore the reducing agent. In redox reactions, we will always have an oxidizing agent and we will always have a reducing agent. And finally, given that oxidation and reduction occur together, reducing agents and oxidizing agents come in pairs. You can't have one without the other. If you identify one reactant as a reducing agent, then another reactant must exist that is an oxidizing agent. In summary, you will have surmised that the term redox is derived from the terms reduction and oxidation. Redox reactions involve the transfer of electrons from one substance to another substance, where one or more reactants loses electrons and one or more reactants picks up or gains those electrons. Loss of electrons is referred to as oxidation, while the gain of electrons is referred to as reduction. And our oil ring mnemonic at the top right is very useful in remembering which is which. Oxidizing agents are reactants that cause other reactants to be oxidized, and they are themselves reduced in the process. And reducing agents are reactants that cause another reactant to be reduced, and they are themselves oxidized in the process. And we will end with one last thing worthy of consideration. How can we identify redox reactions? How can we tell if a particular chemical reaction involves electron transfer with reactants gaining and losing electrons? That is the subject of the next video in this series.